Hello everybody and welcome to Advanced Functions. Today might be our last lesson because today we're actually going to be covering chapter 8.4, which is talking about inequalities of combined functions. Since we've learned how to combine different functions together, we're actually now going to discuss how those combinations can help us solve inequalities. So overall, we're going to be covering one topic, but this topic is going to be split into 3 parts. However, the main focus is of course the techniques you could use to illustrate inequalities. When we're talking about inequalities, it is possible to compare 2 functions of different types. So for example, if you want to find out when f of x is greater than g of x, we've so far only looked at when a function is greater or equal to 0. We have never talked about truly when another function is greater than another function. So this is what we're going to talk about today. In our example, I've provided what f of x is equals to and what g of x is equals to, as you can see here. As I mentioned before, there's 3 ways to actually do this, and I will actually show you all of them. The first way is really simple. You might have thought of it right off the bat when we started talking about inequalities, and that of course is by simply graphing them. If you have the graph of one function overlaid by another function, you could just visually see where one function is greater or when the other function is less than a different function. So of course, this method has a few drawbacks. First of all, when you're working with complex functions, like here we have a third degree and a second degree polynomial function, those pretty simple, we don't have to worry about it. Usually where the problem comes in is, for example, when this can't be factored or this can't be factored. We could also have functions, for example, instead of this being a third degree polynomial function, this could have been a sine function. And then if that sine function had different transformations on it, it'll get really complicated to draw that function plus the g of x function and try to understand where one function is greater than the other. However, if you are dealing with simple parent functions, for example, x squared and sine of x, that process becomes a lot more simpler and you could of course use it. Also, another problem that might occur is the fact that for certain combination of functions, you won't have distinct points. For example, you won't have a whole value for x and a whole value for y. They might be irrational numbers. And in that case, you can't simply look at a graph and point out that that is the square root of 2, for example. You'd actually have to do some algebraic evaluations to find that value. With that being said, that is why we have 2 other ways to talk about these functions and how to solve them. The first other way that we have is by analyzing the difference function. So the difference function, as you can probably guess, is simply the difference between f of x and g of x. So the way we obtain it is we honestly just move g of x to the other side and we get f of x minus g of x is greater than 0. So using this format, we can actually substitute the 2 functions that we had. So we're going to substitute f of x, and here's g of x, open the brackets, simplify, and we get a new function. This function is also a third degree polynomial. However, since it is now pretty simple, we can actually use the strategies we've learned back in chapter 1 and chapter 2. Those strategies, if you have forgotten, would be like your factor theorem, where you'd find out the factors of a and b, then you'd figure out all the possible combinations of b over a, substitute those into your function, and figure out when they equal to 0. If they equal to 0, that means it's a root of the function. So using that root, you can factor this equation. Once you fully factor it, you can make an interval chart and analyze the function then. Again, that might sound a little bit complicated, and it is, but you won't be doing a lot of these types of questions. This might be like a 1 or 2 question on your exam and or test. They cannot possibly give you like 10 of these to do in the span of an hour. However, it is still really important that you understand how to do them, because if you don't, or if you struggled back in chapter 1 and chapter 2, that is really gonna affect you in chapter 8. That's why I always tell you to go and review those other chapters, just so you know that you will be confident with all the material that is required for chapter 8. Now, if you understand this, I actually want to talk about the third way. The third way to solve these types of inequalities is by analyzing the quotient function. So again, the quotient function sounds pretty simple. It is f of x divided by g of x. You might be wondering why we would want to even analyze this, but considering that this is a fraction, and it is technically a ratio between f of x and g of x. When f of x is greater than g of x, we should be getting a value that is greater than 1, right? And if g of x is greater than f of x, then we should be getting a value that's less than 1. So using that definition, we can actually start analyzing these functions in a different way. So here, I've actually, again, plugged in the values, and I got to this point. As you can see, f of x cannot be factored. That gives us a little bit of a hiccup trying to solve this algebraically, because we don't actually know the formula for finding a root of a third-degree polynomial function. All that we've talked about in chapter 1 and 2 is if it is non-factorable, you'd have to graph it. So in this case, you would have to graph the function. Again, this is true for any inequality. If you can't solve it using a pen and paper, plug it into a graphing calculator and it'll give you the answer. I will show you this function graphed in a couple of moments so we can actually compare all 3 strategies and see whether or not our answers or our steps are correct. Okay, so here I've actually graphed what f of x is equals to and what g of x is equals to. Using our first method, we could just find out where they intersect. So let's try to find those points. Point 1, point 2, point 3, there you go. So now we're talking about when f of x is greater than g of x, right? So between these 2 points, it clearly shows that f of x is greater. So our first bound of numbers would be between negative 9.772 and negative 1.228. Our second bound of numbers would be between this point and it seems like positive infinity. So those should be our answers. Again, if we actually want to look at what these numbers are, like that is not a pretty number. This is not something you'd be able to tell by looking at the graph. Like you could tell it's pretty close to 10, but you would never be getting negative 9.772. So if that was the answer, we'd have to look at the other 2 methods. Here is method number 1, which was the function of f of x minus g of x. Again, in our form, we made it greater than 0, which actually gave us the bounds. But if we want to just analyze these, we would look, where is the function greater than 0? If it's greater than 0, that would mean it's above the x-axis. So in this case, it is greater than 0 between negative 9 and negative 1. Same answer as before. Now from 2 to positive infinity, it's also greater. Again, if you want to prove that, there you go. Greater than. So, as you can see, that one worked. Again, putting in the 0, all that does is actually put in the graphs for us. This means that the values are not included, in case you forgot. If there was greater or equal to, as you can see, it becomes a straight line, and that would mean that these values are actually there. Desmos has one fatal flaw with these types of notation, and that is it doesn't give you the values anymore. As you can see, now you have to scroll in, and then you'll be like, oh yeah, it's close to negative 9.772, but this takes a lot of time, and you won't be you don't need to do this for all of it. So I usually never include these and just look at the values here. Now let's actually look at the graph of the quotient. So here it is pretty difficult for us to actually draw, right? We had a slanted asymptote, we have a vertex that's not in the middle. Again, these three things are actually something I told you would not be tested upon because they're really difficult to understand and actually comprehend. But let's actually look at this question. So as we know, if f of x is greater than g of x, this function should be greater than 1. So it is greater than 1 between, it seems like there's here and positive infinity, right? That's what you would want to believe. However, let's actually look at the graph. As you can see, this function is also negative over here. The reason for that is because our function is actually having a negative g of x or f of x component during these operations. So let's take a look at that. F of x and g of x. Over here, g of x is negative. So when we divide by a negative, of course, our function is going to be negative. Over here, again, g of x is negative, but f of x is negative here. So those two things combined produce a bit of a struggle for us to graph this function here. Another really important thing for us to understand is the fact that we had two x values where the function was not defined, right? Like g of x cannot be defined at -4 and 3 because we can't divide by 0. So there you go, we have two asymptotes there. If we were trying to actually identify what happens during those two asymptotes, we would plug in the values for 3 and -5 into our respective equations and try to see what happens there. Another really important thing is that if we were to actually graph the function, we're getting this as our answer. As you can see, it's not really something that we were expecting because it is different than this function here. This value is completely excluded and so is this value over here. Again, the point of that is because our function is actually negative during this part here. So if you wanted to fully analyze this part of the function, we will have to do the following. What you would first do is actually find out where f of g of x is equals to 1. Those values are right here. As you can see, they're not really the nicest numbers. It doesn't actually tell you what they are. Perhaps if we put -1 is equals to 0. Nope, still there. But this actually lets us find what those values are. There you go. With these values here, we can actually try and understand how the graph behaves between the values. So you take these three values, plug them into your equation, find something to the left and to the right, and then you'd be like, okay, I've done that. So now we've actually found out that our graph would be greater than 1 when we have a positive part over here, like we have here, and how our function also has a positive part over here. Again, this is pretty complicated compared to this method over here. That's because it really wasn't made for it. The second method here actually is a lot more beneficial when we have a different type of function or different numbers for the same type of function. So let's actually take a look at that. For this example here, I've actually let us have a different f of x and a different g of x. As you can see, they're both now order of 3 polynomial functions. I made sure that all of them can factor. And so once you go through the factor theorem and actually find out the factored form of these two equations, we get this: x minus 1 plus x plus 2, x minus 4 divided by x minus 1, x plus 2, 3x minus 2. two of these factors are the exact same thing, right? So we can cancel them out, but not forget them. Remember, we cannot forget them. This is still not defined. This should be a whole at 1 and a whole at -2. But this type of function we've dealt with before. We've looked at this exact type of function in chapter 3. Remember the ax plus b over cx plus d type of function? There it is. We know how to graph them, we know how to analyze them. We also know that we can actually just graph the first part here and the second part here, and then just use the quotient procedure like we did in chapter 8.3 to analyze those two functions and actually draw it. Either way, whatever method you use, you should be able to find out the answer. As you can see, it's a lot more simpler, this version, compared to this, which is again one of the beauties of this function here. If we were to plug these into a calculator, we would see the following. Okay, so here I've actually graphed the two functions. Again, we could find out where they intersect and then try to understand what function is greater than the other. Like here, it's greater than between these two regions, and then it is also greater below the axis at -2. Again, pretty hard to see without the use of a different method. So here you go. F of x minus g of x gets us this beautiful explanation here between -1 and 1 and -2 and -infinity. Now let's actually look at our quotient function. So here it is. You know, it seems pretty good, right? Here's y is equals to 1. We found our intersection. And so we're actually going to be going all the way up there. But as you can see, we have an asymptote. What could that asymptote possibly be? Well, look at the denominator of our function. Here you go, I'll turn it on. See the same function? 3x minus 2. So our asymptote should be at x is equals to 2 over 3. Again, there you go. We graphed it. Now, we were talking about when it is greater than 1. So it's clearly greater than 1 between these two regions, right? However, what you might notice is that this region here doesn't correspond to this region here. And there's a big reason for that. The problem with these two equations is this part here. We said that x plus 2 and x minus 1 have cancelled out. But, as I told you, we need to still remember them. So we should have a whole at x is equals to 1, and we should have a whole at x is equals to -2. So at x is equals to 1, let's see if we could reach it. X is equals to 1. Somewhere over there, we would try to find the value. The function here is not going to give us 1 because the denominator would not have a value, but these two functions would. At x is equals to 1, we have an intersection of, let's see, 1 and 1. So you can see that should be our limit. We could then talk about what happens on this side between the two functions. As you could see, f of x is still greater than g of x, and so that should also be included in our answer. Then we also need to talk about the other two wholes that we have. We have 4, we have -2. Going back to here, we should have a whole at 4. Let's get rid of these two functions. Is there a whole at 4? No, there's not. Oh, well, sorry, not at 4. It should be at -2 and then 1. So at -2, is there a whole? There you go, there's a whole. We also need to understand what is actually happening at this whole. At the whole, we would input 2 into this equation, 2 into this equation, and we would compare the answers. As you can probably guess, we're gonna find out that f of x is actually greater than g of x. And so that point should actually have been included in our answer. From this point forward, we could take, for example, this port here, plug that into our equation, and you'd also see that it is positive. These two values multiplied together should give us a positive number that also should be greater than this one here. For that reason, we can actually expand on the definition that we got for this one. Like again, if we put it just greater than 1, we're not getting the full picture. We're getting like half of it. So you need to further analyze what happens at those holes, if there are any holes. But either way, your answer should be the same. It should be this one here. The real usage of these of the third method could be pretty darn hard to understand, because as I've showed you in 2 examples now, you still have to do extra work to fully find the solutions. But understanding it and how it could be used, for example, finding the quotient of a cube divided by a square, you would just get a simple line instead of a polynomial function, and that type would be pretty easy to analyze. So again, what I mean by that is instead of having this as being our f of x, we had x cubed and this was x squared. Graphing these two, we get this function here. So you can see it says it's greater than whenever it is greater than 1. This also proves by this function. Let's see if this one finally works. Oh look, it does. And it's much easier to see it in this one, because all we're doing is x to the power of 3 divided by x to the power of 2, which is equals to x, right? When is x greater than 1? Oh, after x is equals to 1. And so that gave us a really simple and quick answer. The most important thing that you need to take away from this is that every function inequality you will encounter within this chapter, you'd have to use one of these type of methods. If it's a really simple one, like this one here, you'd use the third method. If it was sine of x divided by, or like sine of x, and then like, let's see, what do we have here? Let's do a log of base 2 of x. These two, we can't really use any algebraic solutions on them, right? Like, it's not like dividing sine by the log of something is going to give us a pretty answer. So the only solution you actually have is to graph them and then analyze. Nothing is stopping you from bringing this to the other side and actually graphing the function here. But again, dividing them might not be the best solution. Lastly, if we just had like x squared and then x, these two you can graph by hand and you could just see where those two qualities stand true. Which other method you use, try to think of it beforehand. Don't use a method that doesn't fit, because you will spend a lot of time trying to understand how to find all of the parts of the function. Like again, like this one here, you have to do so much more analyzing than is really bargained for. But either way, let's move on to the homework. Hopefully you've enjoyed that little demonstration of the 3 methods using Desmos, but now let's actually talk about the homework. I have assigned 4 questions here. Like 2 of them are going to be focusing on knowing how to solve the inequalities algebraically, and the other 2 are actual word problems. As with every other chapter, we've been dealing with, for example, cost and revenue, where those 2 could be combined functions, and so that is actually what's happening here. In this chapter, you're more or less going to be talking about when something is greater than a certain value, or when it's less than a certain value. Again, just using the same methods that we discussed today, you could easily solve all of these questions. With that being said, thank you for coming to today's lesson. Hopefully you've enjoyed chapter 8.4. Chapter 8.5 might be a really short video because it really focuses about modeling different real-life situations with combined functions. We've already done some of that during our chapter 8.2 and chapter 8.3 material. but I'll still try to cover the most important components of that chapter. So again, thank you so much for coming today, and I hope to see you next time. Bye bye!